Hello, and this is my video for test 3, video 3. So here the first question is chapter 16, problem 25. 25 is asking use the following data to calculate the KSP value for each solid. In part A, it's asking the solubility of CaC2O4, and it gives us the solubility, which is 4.8 times 10 to the negative 5 mole liter. So first we begin to write the equation for it. Since this is a strong electrolyte, it's going to completely dissociate when mixed with water or dissociate in a liquid. So we get our equation that is CaC2O4 solid. Then we get Ca2 plus aqueous plus C2O4 2 minus aqueous. Here we can start writing our ice chart. So we know it's ice. So for the solid, it doesn't really matter. It's just going to equal to 1. So we know the initial concentration is going to be 0 since it wasn't given. Then we know it's going to be S. Then for E, it's going to be S and S. And we know that KSP is going to be equal to the concentration of Ca2 plus times C2O4 2 minus divided by, since the CaC2O4 solid just becomes 1, it's going to be over 1, but that's just to write it out. So we write this, we start plugging in our values. We get S times S, which is just S squared, is equal to the KSP. And we know the solubility is 4.8 times 10 to the negative 5, and we just plug that value in at our S. So we get 4.8 times 10 to the negative 5 squared is equal to our KSP, which our KSP is equal to 2.304 times 10 to the negative 9. That's our KSP for part A. And for part B, it's asking for Bi, iodide 3, solid. So here we write our equation again. Bi3 completely dissociates to Bi3 plus 3I minus. And make sure to make the states aqueous and aqueous. So here we do again our ice chart. So we're going to ice turns into 1 or 0, or it's basically just 1. So we get 0, 0, 1, or S and 3S. And in the equation, we use our KSP is going to be equal to Bi3 plus times 3, no, not 3, I minus cubed. And we start plugging in our values here. We get S times 3S cubed. Here we could write this as, or 3S cubed is equal to 8. Okay, then right here we could just plug in our values, which is, we know our S is for Bii3 is equal to 1.32 times 10 to the negative 5. 1.32 times 10 to the negative 5 times 3 times 1.32 times 10 to the negative 5. All this cubed. And then we get a KSP value that is equal to 8.20 times 10 to the negative 19. Okay, and this is number 44. Here it's asking the KSP for lead iodide PbI2 is 1.4 times 10 to the negative 8. It says calculate the solubility of lead iodide in each of the following. Part A, water. Part B, 0.10 concentration of PbNO32, and part C, 0.010 NaI. So we're going to start with part A, water. So here, part A, the NH2O. So we know for H2O, it's just going to be Pbi solid, and it's going to completely dissociate. So it becomes Pb2 plus aqueous plus 2I minus aqueous. Here we could use our ice chart. So ice. So this doesn't really matter. Here the initial concentration is just 0, 0. Then it's going to be N. Here an S and 2S. And we're going to S, 2S. We know the KSP is going to be equal to PB2 plus times times I minus squared. Here we plug in our values, so we know that it's going to be S times 2S squared is equal to, and here above our KSP is given, is 1.4 times 10 to the negative 8, so it's going to be equal to 1.4 times 10 to the negative 8. And plugging all the values into our calculator, our S should equal to 1.5 times 10 to the negative 3. That's the solubility in water. And in part B, it's asking in 0.10 milliliter in PbNO32. So for part B, in 0.10 PbNO32. So first, initially we're going to want to set out the equation for this. So we know PbNO32 is going to completely dissociate also. So it's going to be something like this: Pb2 plus aqueous plus 2. Oops, did not mean to write I. So plus 2 NO3 minus. Here, the PBs are, it's going to be a 1-to-1 ratio. So 0.10, 0.10. And this one over here is going to be 0.20, but we're not going to really use this one over here. So we do our rice chart again. So we get PBIS and PB2 plus aqueous plus 2I minus aqueous. We do our ice chart. This one's going to be 1, or basically just 0. So instead of putting our initial concentration at 0, as before, we're going to do our initial concentration as 0.10. Then this one's also just going to stay 0 since we weren't given any values for it. So this one's going to be S and 2S. So it's going to be 0.10 plus S and just 2S. Here we already know our KSP. KSP is equal to PB2 plus times I minus squared. Plug in our values here. We get our 0.10 plus S times 2S squared is equal to 1.4 times 10 to the negative 8. Here, just to save on time, once we plug this all into a calculator, we should get that S, our solubility, is equal to 1.9 times 10 to the negative 4. Okay, and for part C, it's going to point 0.010 m of NaI. Here, it's also going to be really similar to what we did before. So it's going to be 0.01 m of NaI. I. So here we're going to write our equation. NaI S goes to Na plus aqueous plus I minus aqueous. So here it's going to be 0.01. It's a 1-to-1 ratio, so our concentration is going to be 0.101 and 0.010 m and m. So again, we're going to also do our rice chart once again. So we're going to get PB I to aqueous goes to PB 2 plus aqueous plus 2 I minus aqueous. So we're going to do an ice chart once again. So we get ice. So this doesn't really matter. This one's going to be 0.010 m S 2S. And we're going to add them up. So S 0.010 plus 2S. We plug it in for our KSP. KSP is going to be equal to S times 0.010 plus 2S squared is equal to our 1.4 times 10 to the negative 8. And once we plug this into our calculator, we should get the value of our solubility is equal to 1.4 times 10 to the negative 6. Hello, and this is number 55. So here, number 55, a solution is prepared by mixing 100 milliliters of PbNO3 and 100 milliliters of 1 molality of an AF. And here it's asking, will PbF2 solid with its KSP value precipitate? So here, step 1, we get our concentration of each of these values. So we're going to use our dilution equation. So we're going to start with PbNO3 2. So here we're just going to do 100 milliliters times 1.0 times 10 to the negative 2 over 200 milliliters, the total volume. So here it should get you 5.0 times 10 to the negative 3 molarity. So, and we're also going to do it for NaF here, and it's also going to be really similar, 100 milliliters times 1.0 times 10 to the negative 3 over 200, which gives you 5.0 times 10 to the negative 4 molarity. So here we know in step 2 we gotta know the concentrations for respectively for Pb and F. So first we know they completely dissociate. So first we're gonna start with the Pb NO3 2 aqueous, and it's gonna go to Pb 2 plus aqueous plus 2 NO3 aqueous. Here we're trying to find the concentration for Pb, so they're 1-to-1 ratios, so it doesn't need to be balanced. So we know the concentration here is 5.0 times 10 to the negative 3 and 5.0 times 10 to the negative 3. We're also going to do the same for NaF, so NaF goes to Na plus aqueous plus F minus aqueous. Also 1-to-1 ratio, so we know it's going to be 5.0 times 10 to the negative 4 and 5.0 times 10 to the negative 4. Here, now we get all our values, our initial concentrations for F. So, oops, I wrote the concentration here for Na. So, for our initial concentration for F is 5.10 or 5 times 10 to the negative 4. We're going to use them in our rice charts. But first, we know that if Q is greater than a KSP, then it will precipitate. So first we gotta start our Y chart. So it's asking for PbF2 solid. So we know it's gonna go something like this: PbF2 solid. It's gonna go Pb2 plus aqueous plus 2F minus aqueous. Here we start with our rice chart. So ice. This one isn't gonna matter. So we gotta find our Q. So what really matters for Q is just the initial concentration. We could ignore these ones at the bottom. So our initial concentrations are both 5.0 times 10 to the negative 3 and 5.0 times 10 to the negative 4. So our Q is equal to Pb2 plus times 2 or F minus squared. Plugging in our values, we get that it's 5.0 times 10 to the negative 3 times 5.0 times 10 to the negative 4 squared. Plugging these values into our calculator, we get that Q is equal to 1.25 times 10 to the negative 9. That's our Q value. So we go back up here, and our KSP is 4 times 10 to the negative 8. So 4 times 10 to the negative 8. Our KSP, our Q. So our Q is less than our KSP. This means that PbF2 solid will not precipitate. Okay, this is chapter 17, number 68. So first, in part A, it says calculate delta G naught. So for this reaction, the GF values are POCl3 gas and POCl3 gas are 502 kilojoule mole and negative 270 kilojoule mole, respectively. So first, we're going to begin with our equation. So we know our change, or data G, is equal to the sum of number of moles times our G F minus, or this is of products, minus our sum of the number of moles times the GF of reactants. Okay, then reducing all this down, it just reduces down to 2 times negative 270 minus 2 times negative 502. In the end, this is going to spit out a positive number. So our delta G naught is equal to a positive 464 kilojoules. So that's for part A. In part B, it's asking if the reaction is spontaneous under standard conditions at 298 Kelvin. So, since our G is positive, this means that the reaction is non-spontaneous at 298 Kelvin, or in other words, standard conditions. Then we proceed to part C. The value of S of the reaction is 179 joule Kelvin mole. At what temperature is the reaction spontaneous at standard conditions? Assume that the that triangle H naught and S do not depend on temperature. So first, part C, we start out with, we give our S naught is equal to 179 point joule Kelvin. And remember, this isn't in kilojoules, so we're going to do a conversion later on, but we're going to remember this is in joule per Kelvin, not kilojoules. So we know in this equation our delta G naught is equal to delta H naught minus temperature times times S naught. So it's asking for standard conditions, so our temperature will be 298 Kelvin. So we manipulate this equation, so we know that H is going to be equal to the change in delta G plus the temperature, the change in S naught. And we use the G value we got in part A. So our part A, so we use 464 kilojoules. So we know that delta H is equal to 464 kilojoules plus 298 Kelvin times 0.179 kilojoules. And our delta H here should be equal to 517.34 kilojoules. Then we continue on. It's asking for our temperature. So once we find our H, we know that our temperature, to make it spontaneous, is equal to the H naught over S naught. So we get our H from here and our S from up here. So plugging in our values for these, we get 517.34 kilojoules divided by 1.7 or 179.179, and we get that the temperature is 28,090. So 28090.17, but this basically rounds up to 28090 Kelvin.